Hello everyone, thank you for attending this session. In this session, we will discuss one of the most important design patterns regarding the microservice architecture. We'll discuss more about the leadership design pattern, how to implement it, and the most well-known use cases. And we will simulate how the leader can be elected within a set of instances, and we will tackle hands-on the implementation using Java source code. So let's move forward. Number one, we will start by the meaning of leader election. In the distributed solutions, sometimes you need to have only one instance that running and act as a leader to perform specific tasks. Why we need such an approach? That because of having multiple instances that running for the same purpose may cause contradiction and inconsistencies of the implementation. This is related to a set of proper use cases. So sometimes, in some cases, you need to have only one instance that running for specific job. How can we simulate that? Assuming that we have running one microservice over the cluster, and within the cluster we have the scaling approach, and we have implemented to have 4 instances of this microservice. So accordingly, if we have to implement the leader election, we will select one of the instances to be the leader of the bots in order to take the responsibility for performing such a task type. So what if this leader fail during the execution of the operations? In that case, we will have the resiliency approach that this selected leader will be terminated, and then another leader will be elected in order to have resiliency of the solution. So moving forward, what is the most well-known use cases regarding the implementation of the leader election design pattern? Sometimes for the centralization of the locking approach, we need only one instance to take the leadership for implementing the locking mechanism across all the instances of the microservice, because you will cache this, and if you are using application level cache, each bot has its own cache, so it will not notice any changes on the cache level if you are caching the locking mechanism over the application layer. So having only one instance will support your mission to have one centralized caching that implement the locking mechanism. Number 2, the caching warm-up and refresh. What do we mean by the caching warm-up? The instance that take the responsibility for pushing data to the cache, and the refresh also the bot that take the responsibility for the eviction and the update of the cache, in order also to have only one instance for the implementation. And the third use case is to implement the small caching objects like the lookup screens. You can have only one running bot for the cache. So that will support your mission to have one unified caching model across all your microservices, which we will tackle this case in depth here after finishing the use cases. And then finally, the distributed jobs, in order to prevent overwhelming of all the resources in implementing the scheduler jobs. Maybe you have to implement scheduler jobs to be performed at night, like transaction closure procedure, like issuing reports, like sending notification to customers. You don't need to overwhelm all the infrastructure to implement the same job. Just one instance is sufficient, because if all the bots are executing the same jobs, it may contradict, and also it may duplicate the execution, and you may impact the infrastructure by applying locking mechanism, which will impact the infrastructure layer and the database layer. So you are moving the risk that can be mitigated using the leader election design pattern, and you will overwhelm the database by having different locking mechanisms which will cause failure on the implementation due to the long time of the deadlocks. So moving forward, we will select one of the use cases, assuming that we will implement the caching approach at the application level for the small caching objects, assuming that we will implement it without leader election. Let's see what will be the impact. Assuming that each bot will initiate the caching. So at this bot, you will cache object with 10 records, and here the same, and at bot 3 the same, and the same for bot 4. Due to the startup, during the startup of each bot will start the caching after the other bot starts, which may lead to contradiction and inconsistency of the data across the microservices. So assuming that this is number one, assuming we have 100 microservices and you have 10 pods, 10 instances per each microservice, that will lead to have duplicated objects of the caching, which may lead to resource consumption, which you are not managing your infrastructure resources well. Because you are duplicating the cache, you are consuming more memory, you are consuming more CPU for handling the cache across the application. This is number one. Number two, the data consistency across the bots itself. Assuming that bot 1 start at minute number 1, and it cached around 10 records, and then bot 2 start after the first bot by 1 minute. But during that startup, there is update on the database and there is new insertion. So the cached instance on bot 2 will be totally different than bot 1. And assuming that bot 3 take place for startup after bot 2 by 1 minute, so there is additional CRUD operations take place over the database, so it will be totally inconsistent cached object over the different bots, as each one of the bots have different instance of the cache. So that will lead to the inconsistency of the cached objects, which may lead to instability of your solution, as you have to manage different instances within your logic, as you have duplicated instances of the cache. And that takes us to the next point, which the memory pressure over your infrastructure. Due to having around 1,000 cached objects, you will consume more memory and more CPU to manage these resources. And for sure, since you have different instances, you don't have one centralized repository of the cache, which will lead the instability of the solution. This is one of the use cases that you can adapt and use the leader election design pattern within your distributed solution. So for the distributed lock, you can implement the same. For the small cached objects, you can implement the same. For the distributed jobs, you can implement the same approach to utilize and adapt the usage of the leader election design pattern. So how this implementation can take place? Let's move forward. Number one, you will inject the dependencies within your BOM XML file, and then you can enable the leader election in your application YAML to add the annotation for implementing the leader election design pattern. And within your implementation class, you will inform your implementation class to be leader aware, and then one instance of your bots will take the responsibility for implementing such job. So by implementing the leader election design pattern, you will be in the safe side to utilize the resources to have one unified instance of the solution that manage this critical practices, which should take place within your solution. As we mentioned, the distributed looking, the caching warm-up, and the refresh, the small cached objects, and the distributed jobs.